Good evening, everyone. We're going to go ahead and start into Unit 4, Thermodynamics/Thermochemistry. Now, in order to understand what's going on in this unit, we're going to have to cover some things that will usually be in other units, but we're going to sort of roll them in together. Now, this is going to be more of the theoretical side, and then as we get further into the unit, you'll actually see where the calculations and things start to play a role. But started off with a nice little chemistry pun. Why is a hot bracelet more valuable than a cold bracelet? The hot bracelet has more joules. Now, of course, we're going to be talking a lot about joules in this case, but in this terms, not of course, not the precious stuff that we usually think about and pay lots and lots of money, but the energy units. Now, Section 1 learning goal. I can predict the atomic properties or predict atomic properties based on the position on the periodic table. This is going to be the second goal that we have on our tracking sheet, and we're going to continue to move forward starting here. Now, what is a periodic trend? That's going to be the goal of what we're actually going to be looking at here. And we're going to look at patterns that we can use on our periodic tables and whether we can use these patterns in order to predict the type of bonds that will form or how much energy will be needed, and do some comparisons of compounds and atoms. So the first one we start off with really isn't one that we have to pay too much attention to, but it is a pattern that we're going to use, and that is atomic mass. Now, if you go back to when we talked about in Unit 1, where we dealt with Mendeleev and his original idea of how the periodic table was set up, he set it up according to atomic mass, figuring this is the best way to go about it. Now, how do we find this? It's usually on the periodic table, already at the bottom of the box. And it just gives us the average atomic mass for the protons and neutrons. As a basic pattern, we need to know what happens within the group, so from top to bottom, and what happens within the period from left to right. So in this case, reading our regular periodic table as we would, we see that as we go from top to bottom, it gets larger, it increases, and in the period, if we go left to right, it's going to also increase. Now, is this something that would be challenging for us? No, but just to give us the idea, look at again atomic number, looking at the number of protons, and in a neutral atom, the number of electrons. We're going to see the same type of pattern. Increases top to bottom and increases left to right. Now let's get into the actual trends that we're going to have to worry about here. First one is going to be ionization energy. Now, when I think about ionization energy, I usually think of it as a thief. Why do I think of it as a thief? Oops, spelled thief wrong there. Don't follow that one. Thief, I-E-F. Okay. Now, when we think about ionization energy, this is the amount of energy needed to remove or to steal an electron from an atom. So we're going to notice and start to see little bits of a pattern that are going to be seen. Well, let's look at what happens in the group. As we look at what happens from our periodic table, we go from our metals here all the way over to our nonmetals. We're going to see that from left to right, it's going to increase. Now, I drew my arrows here with the largest part of the arrow pointing where the largest values would be. If I'm going to compare this or look at this idea, I notice that I have in the group that it decreases as I go from top to bottom. Therefore, whatever element is here at the top of this column is going to be the one that I can use to compare my other values or other elements to in order to see which one would have the higher values. This is going to play a role in our bonding, especially because we're going to notice that our metals over here, remember those that give away those electrons, are going to be more and more willing to give away those electrons than give away those outer electrons so that they can become just like our noble gases here. So at the top of this group we have helium. So helium is actually going to be I use it as a comparison. So if I'm given 5 different elements and asked to put them in order of increasing ionization energy, first ionization energy, then I know I can compare it to helium. Now, I want you to notice that there I said you can have first ionization energy, first IE. You can also have second and third and so forth. Now, what does that actually mean? Well, how much energy does it take to take away the first electron? And what about the second one? Depending on the group that you're dealing with, you'll actually find that there'll be a little bit more of a challenge. What do I mean? If I go to my group 1 elements here, say sodium, sodium is going to be willing to give up that first electron very easy to become a sodium plus. But after that point, it's going to have what we call an electron configuration that's similar to a noble gas. This is what it wants. This is going to be lower in energy for sodium. So if we want to have, say, for the second ionization energy, it's going to be much higher because now we're dealing with what are called the core electrons. Now, on the other hand, if I have something like magnesium, magnesium would have a lower second ionization energy than sodium would. Why? Because it actually has those two electrons there on the outer ring to give away. And you wouldn't be getting into those core electrons until you've given away or taken away that second electron. So we're going to start to see how and why the atoms bond and react the way that they do. Now, next we move on to atomic radii. Now, atomic radii is what we call 1/2 the distance between two nuclei. It's usually measured in nanometers or sometimes in picometers, which are very, very, very small. Now, the question is, why in the world do we actually look at this as 1/2 the distance? Well, let's take a look at our diagram here at the bottom. If I have two atoms by each other, we know that they don't really have an outer boundary, I guess you would say, a hard outer boundary. If we look at two clouds when they merge in the sky, it's not like you see them bump into each other and bounce away. They sort of merge into each other. Well, that being the case, this is the same thing we're dealing with our atoms. Because the electrons are moving around, moving around, moving around, we have to see what is the distance halfway between where they stop, or where they sit close together. And that's going to give us our actual atomic radii. Now, I remember this one because it's backwards from our last one, from ionization energy. You notice that as you go down the group, you're actually going to increase. And across the period from left to right, it's going to get smaller and smaller. Now, why in the world would it get smaller and smaller as we go that direction? This is going to take us into a little bit of our understanding of what happens with Coulomb's law. But as we go down each row, it's like we're adding an energy level. So our first row, we have our 1 level. Second row, we have 2 levels. Third, fourth, fifth, sixth, and seventh on down the line. Now, along with that, we're spreading out our atoms a little bit. But as we look at what happens as we go this way, we're also adding protons, which is going to have a stronger pull on those electrons. So it's going to bring it closer and closer and closer in. So even though we do have these levels that are added, the further we go this way, the tighter they're holding on to it because we have a stronger charge in the center. We call that the effective, oops, let me write it here, effective nuclear charge. Nuclear charge. Sorry for my horrible writing. Now, as that effective nuclear charge gets larger, it pulls those electrons in closer. And so we're actually going to see this decrease over time as we go left to right. Now, what is my comparison block that I'm going to use if I have to put these in order? I'm going to look at this element box right here, which is going to be francium. So I can look at the other one to see how far, how close it is to francium, and that'll give me an idea. Now, I could go as far as to have a periodic table that has these values on there, but just to predict the general idea, again, we're dealing with general trends here, I can move forward with just the idea and compare it to the location on the periodic table. Now, the last one we're going to talk about in this portion of the video is electron affinity. Now, this is going to be the energy change associated with adding an electron to a gaseous atom. So when I have something like fluorine. Now, fluorine, a monatomic fluorine on its own, is going to want to gain 1 electron. That's going to make it F1 minus, oops, right? Now, when it does this, there's going to be an actual energy change. It's actually going to gain energy or lose energy. In the case of this, in order for this to happen, it's going to have to gain some energy. It's going to have to assume some energy. Now, the further we go this direction, we're going to see that that energy the energy change is going to get greater and greater as we go from left to right. Whereas over here, it would actually take more energy. You'd have to put in more energy to try to get these to actually take this electron. Remember, our metals want to get rid of electrons. They want to try to get rid of it so that they can be like our noble gases. So it's going to be a harder fight to give them, um, smaller amount of energy change, in order for them to actually take on an electron. Whereas here, we're going to actually see that the values are going to be higher, that they're going to gain that much more energy. And not subsequent, as you go further and further to the right, to the right and towards the top. So again, helium would be a good one for us to use as a representative to adjust, or to, not to adjust, to compare to. Having a little moment there. Now, from here, we'll let you go into look over your notes again and make sure everything is in line with what you need. Write down your questions so that when we come into class, we'll actually be ready to move forward in with the next questions. Have a good afternoon and look forward to seeing you.